I like to move it, move it. I like to move it, move it. You like to move it. I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it.
It, in this case, being graphs. What's the fun of having all these different styles of graphs when they're all the same size and all the ones that can be said to have a center are centered at the origin? Let's try to shake things up a bit. Literally, by trying to move the sine graph up. Well, to move things up by, say, 3, then we want to take all of the y-coordinates, all of the heights, and make them 3 higher. We can do this by taking the original function, which I'm going to call f of x, and add 3 to it. So the new function, or g of x, is going to equal f of x plus 3. Since our original function is the sine graph, we can also write this as g of x equals the sine of x plus 3. And that will look like this, the move up that we wanted. Of course, if we wanted to move down instead, we could just add a negative number. But what if we wanted to move left or right? This gets a bit more complicated. In the previous movement, we were changing the height, or y value of the graph. Since y is the output, we were able to change it directly in our function. But we can't do that to move the graph left or right, since this is our input, and changing the function will not change the input we got in. Instead, what we can do to move this is to tell each x-coordinate to take the output from a different coordinate, moving around the graph. This may sound a little complicated, so let's look at what it means. So if we have the sine graph move pi over 4 units to the right, it would look like this. But instead of looking at this as the x-coordinates moving forward, let's look at the change in the height. This point gets its new height from the old height of the point back here, and this point gets its height from back here. So each coordinate now takes the height of the old height of the x-coordinate pi over 4 behind this one. So the new function should spit out the old y for x minus pi over 4, or f of x minus pi over 4. So this g of x equals f of x minus pi over 4, which is the sine of x minus pi over 4. And now we can move up and down and left and right, and by combining this, we can move the graph anywhere we want. This works for pretty much any graph we want to move, and now our graphs are happy, because they can go for walks and play and have fun. But our graphs like to stretch out and relax sometimes too. How would we stretch our graphs vertically? Let's say we want to stretch our graphs to 3 times the size, vertically. Then at each point, we want to multiply the height by 3, so our new y-coordinate is 3 times f of x. This means g of x is 3 times f of x, which is 3 times the sine of x. And now we can grow our functions as tall as we want, or we can shrink them as small as we need. But we still can't stretch them horizontally. So let's look at that. If we draw a function stretched 3 times horizontally, we can compare the heights again. The height at this point used to be the height at 1/3 of this point. Same for that point, and that point, and that point. Can you see why? This means the height for each x is the original height of 1/3 x, or f of 1/3 x. This gives us the equation g of x equals f of 1/3 x equals the sine of 1/3 x. And now we can stretch and shrink and move around and try to do all sorts of things with them. Try playing around with these. Maybe turn the graphs, or flip them, or combine them with other graphs. Let me know what you find. But for now, that's all. See you next time!